and welcome to the podcast of Loughborough University's Institute of Advanced Studies, a podcast where our international fellows discuss the most pressing issues of today that we're all facing and share their exciting research ideas. We hope you enjoyed today's talk. Thank you for tuning in. Good afternoon, everyone. Just about 12 o'clock sharp. Welcome to the IS. I'm Cecilia, director of the IS, and I'm so sorry I'm unable to join you in person today, but I'm sure you've been looked after. Thank you so much for joining. It's an absolute pleasure to host Cecilia today. Cecilia is our residential fellow. It's just wonderful to have residential fellows around. They spend a lot of time with us. They spend a lot of time at Loughborough with our colleagues, with academics, and it's just wonderful to see these collaborations thriving and so many things really being produced as a result of this collaboration. So thank you, Cecilia, for being at Loughborough, and of course, thank you, Weil, for hosting Cecilia. Just a couple of housekeeping rules before we start. So the presentation is recorded and will be available on our YouTube channel and also as a podcast, but we are not recording questions and answer session. So if you have any questions, please feel free to ask. For those of you and for those of us who are online, if you have any questions, please pop them in the Q&A section, and Kieran will be monitoring that. I think that's about it. Well, over to you to introduce Cecilia, please.
All right, thanks, Ksenia. So it's my great pleasure to introduce Cecilia González Tokman. I first knew Cecilia through her work on metastable dynamical system. This is a work which came out of her PhD thesis at the University of Maryland in 2010. Project was suggested by a famous mathematician, Dr. Piat. I then met Cecilia in person in 2011 in Victoria in Canada, where she was a postdoctoral fellow of the Pacific Institute for Mathematical Sciences from 2010 to 2012. Victoria is a very beautiful place. If you haven't been, I recommend it. But probably to the taste of Cecilia, she wanted an upgrade. So after that, she went to Sydney, Australia, and did a postdoc at UNSW, and then moved to the University of Queensland, where she is now an associate professor. Cecilia has made significant contributions in the area of random dynamical systems, publishing her work in prestigious journals such as Journal of European Mathematical Society, Communications in Mathematical Physics, and Communications on Pure and Applied Mathematics. When I look at recent work on random dynamical systems, I always see Cecilia's work is there, not only in references, but also in the text. I mean, it's always nice to see something like this. It says González, Tokman, and Quas framework for multiplicative ergodic theorems. This is something that Cecilia will tell us more about today. Please.
So thanks very much, Will, for the generous introduction and also for the hospitality. It's been a great few weeks here. I also want to thank the Institute team. So Ksenia, Laura, Kieran, Connor, Linda, thanks for all the assistance and also the hospitality. So today I want to tell you about joint work in various combinations with collaborators around the world. So these are Jason Abney, Chantal Blachut, Gary Froyland from UNSW in Australia, Davor Dragicevic from Croatia, Ruan Murray from New Zealand, Rene Oldfield and Joshua Peters from Queensland, also Anthony Quas from Canada, and Julian Cedro and Sandro Vallanti from France. And this will be a math talk, so hopefully by the end you will know a bit more about random dynamical systems and multiplicative ergodic theory. But before we get to that, I would like to motivate this with beautiful video, which really was behind quite a bit of what happened and how this project started. So This is a video done by NASA. It's available online. It's called Perpetual Ocean, and it shows the currents in the ocean. So this is from several years ago, but we can see some of the complexities. For example, there we see the Gulf Stream, so that was discovered by Spanish sailors in the 1500s and used for navigation, but we also know it has an impact on the European climate. But we also see many smaller structures, these round structures called eddies, which are formed and they are mobile. We see them very clearly here. These are called the Agulhas rings. They are formed in the east coast of Africa, and they move into the Atlantic Ocean, transporting water, salty and warm water into the cold Atlantic. So there are many other features, but these are some which can persist for some time, but nevertheless disappear. And when we model this, well, there are different challenges. And what we do in random dynamical systems is we try to accommodate for all the time-dependent factors or all the external inputs, for instance, seasonal effects or noise-like effects such as the wind, into a completely independent system that we call the driving of a random dynamical system. So another feature here, the yellow line is the equator, so there's upwelling there. So of course, if we're thinking of applications, we would have to think not just in 2 dimensions, but in 3 dimensions, so that it would be good to develop some tools which can do that. And finally, here we're getting to Antarctica. So Antarctica is almost isolated from the rest of the ocean by this circumpolar current. And finally, we're getting to Australia. So we see Tasmania right there. Brisbane is very close to the easternmost point. And we see again these smaller eddies, which again are also important, for example, for marine life, as that's where nutrients come to the surface. So anyways, this is just a motivation, and I think it's a good picture to keep in mind, and it will also help us hopefully interpret some of the results, and of course it also motivates some of the questions. So I want to present 3 parts. So first, I will spend quite a bit of time introducing the dynamical systems, random dynamical systems. We're going to build some complexity. I know there are many non-mathematicians in the audience, so we will start. Hopefully it will make sense, and then I will introduce multiplicative ergodic theory, which is the main tool that we have been developing. And finally, I will comment on some stability questions. So let's start with dynamical systems. So I'm going to be talking about systems in discrete time. So if we have in mind a flow, we can just say, okay, we look at it every second or every hour or every month. So we can always get a discrete system out of this. And in the classical setting, this is given by a rule or a function that tells us how the system evolves in one time step. So T says we start with a point X, we apply T, we get T of X. That's the state of the system at one step. After one step, if we want to go n step forward, and we always have the same evolution rule, we just apply T n times. So that's the classical setting. And let me give a very, very simple example, but I think it already captures a little bit of the complexities where we're dealing with when we think about transport. So in this case, we're gonna take T to be just this 2x2 matrix. So it's one very, very simple dynamical system, I would say. And maybe you have seen this type of figure representing what is called a Markov chain. So this is, let's think we have a country which has a city and a beach, and at the end of the month, each person decides whether to remain where they are or go to the other location. And if they do so by, say, flipping a coin with certain probabilities given by the weights in these arrows, that gives rise to what is called a Markov chain, and the evolution of the system is encoded by this matrix, in the sense that if we think of the state of the system as proportion of people at the city, proportion of people at the beach, after once, so for example, if we start with 1, 0, that would mean everyone starts at the city. After one step we multiply, we get these first column, so we expect to find 90% of the people at the city. And if we want to make predictions, we keep multiplying by L over and over. So that would be the case of an autonomous system. If we want to talk about random dynamical systems, so that would be the case where somehow, for some reason, the decisions are taken in different ways. So, for example, maybe there's different weathers, and if it's hot and people are at the beach, it's much more likely to remain at the beach. So random dynamical systems, what the idea is that we have several, possibly many evolution rules, and the way in which these rules are composed is dictated by an external environment. So that's what we call the base system, and we denote by sigma. So the state of the environment, which we write omega, is telling us what's the next rule that we will apply. Okay, and if we think of the ocean, for example, so sigma could be incorporating any seasonal effects and the winds, and even maybe other more complicated factors. So for the experts, we do impose some conditions on this driving system to be able to develop some mathematical theory. And we ask that this is an invertible ergodic and measure preserving transformation. But if this doesn't make any sense to you, let me give you 3 examples that are covered by this theory, which hopefully gives an idea of the scope, the wide scope for this framework. So the first case is, of course, if we just have a single environment, if we always apply the same rule, that's covered here if omega is a 1-point space. We can also have just seasonal forcing, and in that case, sigma would be given by an irrational rotation. And in the case where, for instance, the weather is dictated by the outcome of, say, coin flipping experiments, then in that case, we can also model this in the context of random dynamics by taking omega sequences of just heads and tails and some probability measure. So just to recap, so we have our external system sigma telling us just about the evolution of the environment, and we're going to assume that we have linear evolution rules, like in the case of the Markov chain or the matrix that I showed. But of course, I will come back to this if we want to model like nonlinear systems such as the ocean. Well, how would we get here? But for now, it's just a linear system, and the way in which the system evolves is by composing the different rules according to the different environments that we observe. So this is called the co-cycle rule, tells us how to compose. And there are other names for these types of systems, sometimes also called Q product co-cycles. And there are a couple fundamental books on the subject, which go back to Kiefer and Arnold. I also want to comment, these are related to so-called time-dependent, non-autonomous or sequential dynamical systems. I will briefly comment about this later, but the difference there is that there is no kind of probabilistic rule behind them. In those systems, they are just composing different rules, maybe without any further information. So now, how do we use this kind of linear approach to model nonlinear systems? So this is an idea going back to Ulam. So he is the same who developed the Monte Carlo experiments, and he had an idea to model any nonlinear system with actually a Markov chain. So his idea was to take the state space, for example, the square, divide it into bins, for instance, 16 bins, and then in each of these bins, throw some initial conditions and compute. So the bins are the states of the Markov chain. So in this case, we would get a 16 state Markov chain. And to compute the transition matrix, what Ulam's idea is to look at several initial conditions on each bin and compute the proportion of among those which say remain on the same bin or move across to other bins. So in this example, for instance, you can see that particles starting in bin 1, after one step, they either remain in bin 1 or they move to 2, 3, or 4. So all the other entries would be 0. So of course, this is somewhat simple or naive idea. Perhaps one could try to refine, add more bins, add more trajectories, and perhaps that way get closer and closer approximations to reality. But if one really wants to capture all the nonlinear aspects of the system, that's how we get to what we call transfer operators. So the idea here is that instead of thinking of the evolution at the level of particles, so what happens to an initial condition X, we think of particle distributions. For instance, say we throw some floaters off the coast of Queensland. That could be our initial distribution. We observe what the distribution looks like after, say, 1 day or 1 month, and that would be like the transfer operator applied to this initial distribution. So that's why these are useful to study transport phenomena. Of course, one can write formulas, and for instance, there's this one which relates the transfer operator with the composition operator. But the price one pays here is that in general, when we do this, we are no longer in finite dimensions, we have to go to infinite dimensions. And so that may bring some complications. In particular, even if we have a linear system within infinite dimensions, this can be quite hard to treat. But sometimes we can show some good properties for these systems, for instance, compactness or quasi-compactness, which allow us to, again, gain some insights more or less in a similar way than one would get in the context of matrices. So just for the experts, so quasi-compact in this case means that the spectrum of this operator is always 1, and quasi-compactness would mean that there's a disk of radius k strictly less than 1, so that outside that disk, the only spectral values are isolated, correspond to discrete eigenspaces. So how that is useful to get information about the long-term behavior of the system. So let me move to like an intermediate complexity system. So we're no longer in matrices, we're not in geophysical flows. So we're gonna be talking about, in this case, one-dimensional map. So let's think that the state of the system is just one variable x, and the evolution of the system is given by this graph T of x. So if we start somewhere around 0.25, after one step, we're gonna move somewhere here around 0.5. And if we want to know forward, in the autonomous case, as this first example, we just iterate the same map. So when the map is expanding or piecewise expanding and smooth, the work of Lasota, York, Wrigley, Keller, and Ruel in the 70s and 80s showed that the transfer operators associated to these maps are quasi-compact in some spaces. And so with that, one can recover the long-term behavior of the system. For example, 1 is always a leading eigenvalue, and when it's simple, that corresponds to having an indecomposable system, so ergodic, and the eigenvector associated to that is giving us information about what we call the absolutely continuous invariant measure, but it's very, very closely related to like stationary distribution or steady state of the system. And when we have a second eigenvalue strictly less than 1 in magnitude, we have what is called a mixing system. So let me illustrate that with some pictures. So if we start with different initial distributions as in the figure, and we evolve with the transfer operator, we see that these different distributions are getting closer and closer together. And they are in fact converging to this fixed point. So that we're seeing the steady state of the system, or this first eigenvector of the transfer operator. In the 90s, a group of applied mathematicians in Germany suggested that maybe if one looks at farther into the spectrum, like the second eigenvalue and eigenvector, maybe one can get information about almost invariant sets. So like in this figure, if we have 2 regions of the system, and maybe there's quite a lot of movement within each of the regions, but only very little leakage connecting them. So what they suggested is that the second eigenvector of this transfer operator could perhaps separate, maybe give positive sign to one of these sets and negative sign to the other set. So that's what was, let's say, the situation for autonomous systems. And we can also see, for example, if we look at the, when we say project out the invariant, the top mode, and we just look for the second mode, we can also observe it by just running the system forward. So in this case, we see the separation between the left and the right components. But so what happens in the case of random dynamical systems? So we have similar questions. Can we say something about the long-term behavior? And is there something like an invariant measure or stationary distribution? And if so, okay, can we even say, talk about finer properties like decay rates or limit theorems? And just the picture that we talked about in the autonomous case, it may look something like this scheme. So in the long term, we see convergence to equilibrium. So in the random case, things look and are more complicated, but okay, can we make sense of something even in this situation? Other questions are about the medium term phenomena. So for instance, these structures which may persist for a long time, but maybe not forever. And finally, stability. So of course, if we have some applications in the back of our minds, this is an important question. So what happens when we perturb the system in some way, for instance, because there's noise or model error, or maybe we're using numerical approximations? How does the information that we get, how does it change? So to answer this is that we get into multiplicative ergodic theory. So in one sentence, multiplicative ergodic theorems, when they apply, they provide us with spectral type decomposition for random dynamical systems into nonlinear time-varying modes. So on the left here, we see the picture for the autonomous case that we discussed so far. So maybe this first space or this first mode encodes information about the long-term behavior or stationary distribution or steady state of the system. Maybe the second space encodes information about these nearly invariant components. And of course, there could be more. In the random setting, when multiplicative ergodic theory applies, instead of eigenvalues, we have Lyapunov exponents, and instead of eigenspaces, we have so-called oscillated spaces. And one of the big differences is that these spaces are not fixed like eigenspaces, but rather they depend on time or they change with the environment. And the second difference, but there's still a first space which is mapped to a first space, second space mapped to a second space, and so on. And the second difference is that instead of having information about one-step expansion or contraction, as in the eigenvalue eigenvector equation, we just have information about the long-term rates of growth or decay, which are given by the Lyapunov experiments. So let me again go back to what I think is the simplest example of the multiplicative ergodic theorem for 2x2 matrices. So, and again, let me start with the autonomous case just for reference. So here we're plotting on the horizontal axis time and on the vertical axis the first entry or the probability or the proportion of the population that we expect to find in the city. What we see there is if we start at the top left, so the blue dot there corresponds to starting with the full population in the city. Of course, after one step, we know it's going to be 90%, but we see really quickly it has converged to this value, which is 0.875, which corresponds to this first entry of the eigenvector of the first eigenvector of eigenvalue 1. But also, if we start in the complete opposite situation where everyone starts at the beach, well, initially we have 0, then we have 0.7, and again, very quickly we have converge, right? So this is what is called the Perron-Frobenius theorem. And if we have now a non-autonomous environment, let's start with periodic first, say 3 hot months followed by 9 cold months. What we see if we look at these proportions is, well, we see this periodic pattern. So the periodicity of the environment is reflected in what we are seeing. But if we look carefully, we can also see that after a short time, so if we start in opposite initial conditions, well, initially these values are completely different, but very quickly they have kind of converge, and instead of seeing blue and red, we just see the purple mode. So it's both are evolving in the same way. So when multiplicative ergodic theory applies, what we have is, well, in the case of random systems, the long-term behavior may be complicated in that it reflects the complexities of the environment, but we still have these kind of loss of memory or loss of information about the initial condition, in the sense that, again, we start just seeing this purple mode after a short period of time. And we can think of this purple mode as being the first entry or of the first ocellated space in this case. So it really is telling us about the long-term behavior of the system. So let me say a few words about the history. So multiplicative ergodic theorems were first discovered by Ocelladet in the 60s. So he worked in the context of invertible matrices. Also Raghunathan worked in a different way in the same kind of systems. And as people became more interested in applications, they developed other like infinite dimensional versions, like Ruel worked in Hilbert spaces, and Magnet, Thielen, Liandu, Blumenthal, they worked on Banach spaces. And there are other versions of the theorem, but these are the closest to the setting that I'm working on. And I should say there's also a version of these theorems for non-invertible matrices or operators, but in that case, one recovers in the classical setting less fine information. So it's just called filtration, not a splitting. So that's why semi-invertible multiplicative ergodic theorems were developed by Froiland, Lloyd, and Quast. So in the context of transfer operators, these are often not invertible. So the classical theory didn't apply. And what they were able to do is to show that if the environment system is invertible, but maybe the matrices or operators are not, one still recovers this splitting. So that's what they did starting around 15 years ago, first in the context of matrices, then some operators, and finally, when I joined this group, we developed some results which are more widely applicable, in particular in the context of transfer operators. So I don't want to be very technical, just a snapshot of what these results look like. There are some hypotheses there, and there's some conclusions. So, but let me just say that the idea is basically what I told you in the picture, and of course happy to talk about if people are interested. But let me instead show you what the consequences are. And let me do this again in this intermediate complexity case where we look at, say, smooth expanding maps, or even piecewise smooth expanding maps. And this is something that Buzy studied in the late 90s, early 2000s. There was not multiplicative ergodic theory available in this setting, but let me anyways phrase his results in this language just for comparison. So what he was able to show is that there is this mode that depends on the environment, but still encodes the long-term behavior of the system, in the sense that if one looks at the trajectory and one looks, for instance, at how some observable, if one measures some observable along the trajectory of the system, and one looks at averages, one gets convergence to a spatial average, but the spatial average has to be taken with this ocellated space, let's say your first ocellated space, incorporated there. So in that sense, the ocellated space gives information about the long-term behavior of the system. And again, when the second Lyapunov exponent, which in this case the leading one is 0, when the second one is negative and we only have this leading mode dimension 1 of the top space, we again see this effect of mixing. So again, what happens when we evolve different initial conditions with our transfer operators, what we see there is that the densities there, they start to look much very much like each other, but they are not converging to a fixed point. They are rather converging to this object, which is depending on the environment. So that's the random invariant measure in this case. When multiplicative ergodic theory became available, and again, this was developed first by Froiland, Lloyd, and Quast, having in mind applications to these systems with perhaps nearly invariant or coherent mobile structures, then the opportunity or the doors were open to trying to apply or find examples of these in random systems. And so the first type of result that we got, concrete results, were in the context of metastability, which Well mentioned in the beginning. And yeah, Well is also one of the ones who has developed this area. So in the random setting, we were able to show that one has this metastability in the sense that one can, let's say, separate these two components and some information on the rates through multiplicative ergodic theorem. And we also have another example, which I will mention briefly towards the end. But we also were able to show that one way to approximate these ocellated spaces is using singular value type decompositions. And so this opens up the possibility of using this or trying this in applications. And this is what a student few years ago did. So Chantal Blachut, she went to the website of the European Center for Medium Range Weather Forecast, and she downloaded wind vector field data, use this to build some sort of Ulam approximations, as I described before, and using this singular value type decomposition, she obtained this movie, which shows this is the Antarctic polar vortex. It's known to have suffered this splitting event in 2002, and this is now visible in this using these tools. So I should say this is, if you like, a proof of concept. There are other groups who specialize in using advanced numerical analysis techniques combined with some of these ideas to really track, for example, eddies in the ocean and so on. And these are mostly led by Gary Froylan. Yeah, I've been interested in developing also extensions and refinements of these results along with some collaborators. So let me mention some work in higher dimension limit theorems with Dragicevic, Froylan, and Vajanti. We've also looked at so-called open systems, which is the case when trajectories can escape the system after some time. And these are also useful to study extreme value theory. And that's been with Adnip, Froylan, and Vajanti. More recently, I've been interested in maybe relaxing some of the conditions, for example, uniformity or even the complete randomness. And there's been some work with René Oldfield and separately Davor Dragicevic and Cedro, where we are looking now at some sequential type systems. So we're no longer relying so much on random systems. And this is also related to the project that I'm currently working on here with wild. So some cases where we no longer have this randomness as nicely present. So in the last few minutes, let me say a few words about stability. As I said, the question here is how does this spectral type data, so Lyapunov exponents, oscillated splitting, how does it change when we perturb the system? And again, we have in mind perturbations which could come from model errors, noise, or numerical approximations, such as the Ulam scheme, but there are many others. And I would like to mention some relevant work in the context of autonomous systems by Keller and Liberani. So they showed when we have this quasi-compactness property, we have stability of spectral data in the sense that eigenvalues and eigenspaces change only slightly under perturbations. In our setting, we are thinking of perturbing at the level of the maps or the transfer operators. We keep the environment unchanged, and just a few related works are due to, Ledrapier and Young. They developed some stability results for Lyapunov exponents in the context of invertible matrices, and then Ox investigated and developed the connection between stability of exponents and stability of the splittings, and then Back Spoletti, they developed a semi-invertible version of this result. In the context of perturbations of expanding maps, random perturbations of non-random maps, there's a result by Baladi, Konda, Schmidt, and also work of Bogenschut. And but there's also a warning in the sense that it's known that instabilities can occur. And this was illustrated, for example, in the works of Bocchi and Viana, where one can perturb the matrix, even matrix cocycle a little bit, and get completely different Lyapunov exponents, for example. So first, what we did is we investigate the just stability of this leading mode, or this kind of stationary measure, which of course is very important to tell about the long-term behavior of the system, but it's also quite special to investigate. And we were able to show in joint work with Froilan, Quas, and also Murray that this first mode is stable under various types of perturbations. What we show in that figure are approximations. On each column, we are approximating some of these F omega or Y1 omega slice using different schemes, so Ulam scheme at the top and Fourier schemes at the bottom. So we see quite good agreement across columns. And more recently, with Froilan and Quas in different works, we also investigate the stability in the context of finite matrix cocycles, also infinite matrix cocycles, when we have non-invertible, possibly non-invertible systems, but we introduce some IID nodes. And in the case of transfer operators, the first example that we were able to understand is in the context of so-called random Blaschke products. So these are a class of maps as the ones that I showed. They are expanding on the circle quite regular. And what we were able to show with Anthony Quas is that there are some instabilities. So instabilities can exist in this context, so which was somewhat surprising to see by introducing just quite natural perturbations in some way. We didn't really have to look very, very hard for which perturbations will do the job. Really very natural perturbations were here. But then we understood the instability mechanism, let's say, sufficiently well to be able to really characterize the case of stability. So when is such a system unstable or stable, meaning when are the Lyapunov exponents, say, vary continuously or discontinuously. And we were also able to show that in some sense, stability is generic. So in a topological sense with Anthony Quas, and then there's some work with Josh Peters, where we start investigating this in a prevalent or measured theoretical sense. So with that, let me thank my collaborators, and I leave you with a summary. So hopefully I've convinced you that random dynamical systems provide with a general and flexible framework to investigate systems which evolve under changing environments, for instance, random forcing or seasonal cycles. Also that multiplicative ergodic theorems give us a spectral type decomposition, Lyapunov exponents, and oscillated spaces, which encompass fundamental information about the transport phenomena in such systems, including invariant measures and also mixing rates on fluctuations. And finally, that stability is of central interest for us, especially for applications, because we have a range of perturbations which could arise, and only partial progress has been achieved here, but lots of questions remain open. So with that, thank you for your attention.
Thank you for listening to the podcast of Loughborough University's Institute of Advanced Studies. A quick reminder about how to stay connected. You can find us on Blue Sky, LinkedIn, and Instagram, and you can also watch the presentations on YouTube. The podcast is available on all the major platforms. Please download, share, and most importantly, subscribe. See you next time.